Hi there, everyone. Welcome. Here I am with a small video session on one of the popular, perhaps the very first quantum algorithm, Duetsch-Jozsa algorithm, proposed by David Duetsch and Richard Jozsa in 1992. On the left hand side, you see Richard, and of course, on the right hand side, it's David. Nowadays, this DJ algorithm is regarded as a tie problem due to its rare to non practical usage. Yet, fundamentally, this algorithm is crucial in understanding the quantum computers, in contrast with Turing machines or digital computers from the computational complexity perspective. So here is one nice diagram from internet about quantum advantage. Quantum advantage is essentially a parameter that helps us to gauge or scale problems based on their size or resources. Along x direction, its problem size, and time along y direction is taken. Regardless, it's quantum hype or reality. Theoretically, quantum computers are efficient in solving very complex problems that classical computers might fail to solve due to resource crunch, such as memory or processor speed. And it's not always necessary that one should opt for quantum computers to solve complex problems. There are instances where classical or digital computers are also known to excel in this area. We can even call it black box or algorithm or even oracle from the famous Greek mythology of Oracle of Delphi. So it takes n input arguments as a binary strings in the form of zeros or ones or combinations of zeros and ones, and it outputs zeros or ones. So it is promised that with this n input binary values, if it outputs all zeros or ones, we call it a constant function, or if it returns for the first half of, let's say, 50% of the inputs, if it returns say 0, and for the remaining 50%, if it returns 1, we call it a balance function. Animation explains Duetsch-Jozsa balanced oracle. We input the numbers in the form of binary strings from the left hand side and read the output from the right hand side. Let's assume that the topmost bit is the most significant bit and the bottom one being the least significant one. We are also dealing, in this specific case, we are dealing with 6 bits binary string. So that spans from 0 to 2 to the power of 6, which is 64. Essentially, we have all the numbers, or let's say we have the counter that actually generates numbers ranging from 0, 1, 2, 3, 4, so on up to 64. We first input the 6-bit binary string, that's 6 zeros. So since Oracle is balanced, the return it should return 6 zeros at the output. If it is positive logic, of course, it's 6 zeros, and if it is negative logic, let's say it returns 6 ones. Let's try with number 24, which is from the top 0, 1, 1, 0, 0, 0. So the output is again in the positive logics, it should return 6 zeros, or in the negative logic, it should return 6 ones. Remember, 24 is less than the 50% criterion of balanced oracle. It's less than 32. So therefore, it should either return zeros or ones, 6 zeros or 6 ones. Now let's deal with number 34. Recall 32 is on the higher side of the 32. That is, it falls between 32 to 64. So what should be the balanced oracle supposed to return? It's supposed to return the opposite logic of what it did with the numbers below 32, that is between 0 to 32. For instance, had it returned zeros or ones for numbers between 0 to 32, this oracle now returns ones or zeros. So it's zeros are ones in the previous case, ones are zeros in this case, because the number 34 is on the to the right hand side of the 32, or it falls between 32 to 64. And for number 64, the balanced oracle returns what it did for the number 34, as this number falls between 32 to 64, and this is the second half of the number set or the input data set we are passing on. Also, let's take a look into the Oracle constant or constant Oracle animation. So here is the animation. It's self-explanatory. We have been, feeding the numbers from the left-hand side, and the output is actually read from the right-hand side. For all numbers starting from 0 to 64 in this case, the output remains constant throughout. Either returns zeros or returns all ones, all zeros or all ones, depending upon the type of logic. So here is the typical timing diagram for both the Oracle balanced and Oracle constant of Duetsch-Jozsa. On the top, you see the counter or clock. Each cycle, let's say, represents one. So starting from left-hand side, we read the first cycle is, let's say, 0, second is 1, third 2, 3, 4, 5, 6, 7. And so basically it's ranging from 0 to say 8, or let's say 0, 1, 2, 3, 4, 5, 6, 7. So those 8 numbers. For a balanced function, the 50%, which is 4, should either return 0 or 1, because that's one of the important criterions for balanced function. So you see the 4 starting from the left hand side, the balance negative remained 0 for 0, 1, 2, 3, and from 4 onwards it flipped to 1, and it remained 1 till the last number, which is 7. And below 1 is the positive logic, however you want to take it. It remained 1 till 4 and flipped to 0. But you see the constant function that remained 0 or 1 for all numbers ranging from 0 to 7. Let's look into the Oracle. Now, let's look into the Pythonic classical approach for Oracle Duetsch-Jozsa. I'm importing the random library on the very top, and this is a very custom function, a customized function that transforms, or let's say that converts, a binary equivalent of list of integers, list of ones and zeros, to a decimal number. For example, uh, this is the input we pass on through arguments in the form of tuples. For example, this list starting from uh, index 0 to higher index, that is 1, 1, 0, 0. 1 here being the, or let's say the left hand side being the most significant bit, and the right hand one being the least significant. This number is to be read as 12 because it's essentially 8 and 4, addition of 8 and 4. So let me just quickly show you the thing here. Now this is, oh sorry, okay, let me first run the code. Alright, that's returns 12, the number is 12, and now this is 25 because 16 plus 8 plus 1, so let's try that. That's 25 again. And now let me show you the bottom one, that is 3 ones, MSB being 1 and LSB also being 1, with 1 in the middle. So this is supposed to be 4 plus 2 plus 1, which is 7. This code has already been uploaded to the GitHub link. Here is the GitHub link. I also provided the GitHub link in the YouTube description. Please review and comment. Now let's look into the Oracle part. This is the heart of the algorithm itself. So it takes 3 inputs. One is the number of, in quantum sense it's qubits, but here in this case it's the number of inputs or bits you want to pass in. I'm also passing another argument, that is balanced, so which is essentially a Boolean type variable or argument. If it is true, the function is supposed to return a balanced function, and if it is false, the function is supposed to the function returns the constant function. And I have 2 cases here. One is the best case and worst case scenario. So in the worst case scenario, the computational complexity of this specific code, or let's say the specific algorithm in big O notations is its ON, typically mentioned in the form of ON, essentially meaning the function has to go through n number of iterations to verify whether the function is constant or balanced. So that's the gist here. And the function has, inside the Oracle function there are two sub functions or nested functions. One is being the constant function, which returns either 0 or 1 whenever the function is invoked, and this is a random number itself. It's a pseudo random number. In fact, it's not true random number, of course, as we all know. And here I have another balanced function defined. So please, this code is self-explanatory. Kindly look into the code and you will know everything for yourself. Now the second one being the deterministic verification. So we need to verify the oracle, whether the oracle is performing, whether the oracle is say constant or balanced type. So this method does that for us. So it takes two arguments, n being the same, the number of bits we are passing in, and here we pass the oracle function, and it does some trials. So this is again a binary equivalent of the trial. For example, if it is first trial, the binary equivalent goes let's say 0 0 0 1. If it is third, it goes 0 0 1 1. If it is, let's say, fifth trial, or let's say eighth trial, or let's say 25th trial, it's 1 1 0 0 1. So the binary equivalent of this number of let's say this one, this is the binary equivalent of, and we pass this one to the oracle function here, and the oracle function is actually stored into the oracle state. And now here goes the validation. So if the returned oracle state is not same as the initialized state, that is all zeros, so from the second iteration onwards, it considers it as a balanced function. So in a best case scenario, to verify a balanced function, you just need 2 iterations, or let's say 2 plus 1 3 4 5 iterations, depending upon the randomness introduced in the balanced function. In an average scenario, however, the function has to walk through all 50% of the numbers. In addition to 15% of number, it actually should consider one more number, that is 50 plus 1 number, and then the function supposed to confirm that the function is balanced or the oracle is balanced. In a worst case scenario, however, the function has to walk through all inputs, that is 2 to the power of n inputs. Thereby the complexity in big O notations is order of n, On. And now if this criterion fails, so the function is supposed to be a constant function. In a best case scenario, the function has to just perform 1 iteration, which is extremely rare. In average scenario, however, the function has to perform n by 2, let's say 2 to the power of n plus 2 to the power of n by 2 plus 1 more round or 1 more trial to confirm the function is constant or not. But in the worst case scenario, however, the function has to go through all n number of inputs and to confirm the function is constant. Now let's do the test here. So let me take 6 bits here and first consider the balanced function because let's say first consider the balanced function. Therefore I need to set it to true. Oops. Okay, and let me try for the best case first. All right, now now we are passing the arguments, or let's say the variables. N is balanced and case, and then we store the output of the oracle to oracle function, because oracle function is essentially, oracle is returning oracle function essentially, either constant function or boolean function, however you call it, or based on the input arguments. Now we pass the same here. So to the verify function, we are passing the number of digits, or let's say qubits in quantum sense. But here in this case, it's just classical computer. So we pass the number of bits, and of course the oracle function. Okay, let me rerun the code. Okay, excuse me. So it's a balanced function, of course, from here, and it performed just 2 iterations to confirm that it's a balanced function. Now let's do one more trial, one more round. So in this case, it performed 2 iterations again, 4 iterations, 2 iterations again, 2 iterations. So the computational complexity in this case is 2 because it performed 2 iterations. Now 2. Now if you keep on doing, now in this case actually it performed 7 iterations. That's because we introduced some randomness in the balanced function here. So in a best case scenario, the code actually shuffles all the numbers. It randomizes all the numbers. That's where the computational complexity comes in. Now let me run for one more time. So in this case, it iterated just in 3 trials. Now let's try the balanced function in a worst case. So let me change the best case to worst case. So in a worst case, it performed 33 iterations. Reason being, the moment I set case to worst, there is no randomness being introduced in the numbers generated. That's where the system, or let's say that's where the verify oracle has to crawl through all 32 plus 1 number to gain confidence and tell us that this is a balanced function. Okay, and this will remain no matter how long or how many trials you do. So it has to go through all those 33 elements to confidently tell that the function is balanced. Now do the trial for a constant function. So to define a constant function, we set is balance flag to false, and we try for best case again. So the function performed 33 iterations to confirm the function to the type of to confirm the oracle is constant. So that's in best case. Now let me do for the worst case. So there's no big change for constant function. Typically, it performs all 33. The reason for 33 is 2 to the power of 6 is 64. So 50% of 64, the threshold is 32 plus 1 extra trial to gain the confidence that this is a constant function. Yeah, so this is how we validate it. That's about Duetsch-Jozsa algorithm, a classical approach in Python. If you enjoyed the video, please like, comment, share, and for more such content, please subscribe to my channel and enable notifications. Thank you and stay safe. Until next time.